Generally, when limited data is there, but that is actually not possible, because if you have a very less amount of data set is there, and for that you cannot do very good understanding. Very few problem we can address by this type of region 2. Now generally, if you come to the region 3, actually good data and good understanding, and that is actually, but that is not applicable to the especially in offshore geotechnics, because we generally work out the very limited about the data set, because every data is very costly and time expensive also. So generally we all civil engineering generally fall in region 4, limited data and little understanding, because we generally use very less amount of the data set, and based on that we design. And that means if you have a very less amount of data set, obviously you will be understand the problem very little. So here actually AI, we can use AI, because if you can develop the AI model, based on that, if you one time if you can develop the model, then you can generate many amount of data set, and you can thoroughly understanding the problem. So based on this holding concept, the people, that is the motivation of the using AI in the field of civil engineering. Now, what is the branches of the AI? If you look at, that is, one is that artificial intelligence. First one is the machine learning. So machine learning, it consists two steps. One is the pattern recognition and deep learning. Pattern recognition means basically, if you see the geotechnical problem, pattern recognition means, for example, landslide will occur or not occur, liquefaction will not occur or not occur. That means it's a binary type of problem. Your pattern you are recognizing. Second thing, the deep learning. Deep learning actually, when we are using huge amount of the data set is there, we have plenty amount of data set. For example, if you can collect all the data set of the SPT all over the world, and then you can try to develop a correlation between the angle of internal friction with the SPT, that time deep learning can be used. So that is called the deep learning. Next, the big data and data mining. Big data is nowadays very useful. So they are actually, where actually that big data means there is a 4 V. That is, one is the high volume, high variety, high versatility, and high. So when you are getting very huge amount of data set, for example, and the data will be continuous. For example, today also there are somewhere in the SPT test or institute test going on. So automatically data will come every day, and every day you will get the new data set. So that's the concept of the big data concept and data mining. Next part is the knowledge-based system, that is the fuzzy logic and expert system. There generally we use some rules, if and then rules. For example, if you can see that, for example, if you take the bearing capacity problem of the shallow foundation, if your phi value increase and C value increase, then automatically your bearing capacity of the soil will increase. So that is if then rules. That means if C and phi increase, then automatically the bearing capacity will increase. That they are using in the knowledge-based system. So there are two types of knowledge-based system. One is the fuzzy logic and the expert system. Next is coming, the one is the genetic algorithm, evolutionary algorithm and swarm intelligence. Genetic algorithm and swarm intelligence, that is part in the meta-heuristic optimizations. Meta-heuristic optimization is that generally traditional optimization, we generally got the what is the ultimate solution, but in meta-heuristic optimization only the solution whatever you desired. Generally we obtain whatever our desired solution. I will come to this meta-heuristic optimization in my next slide. So yeah. So if you look at now this artificial intelligence actually is the ability of a machine that initiate intelligent human behavior, and machine learning is the learning computers to process the data in a way that inspired by the human brain. And neural network is the application of AI that allows a system to automatically learn to improve from the experience. And deep learning by using neural network. Deep learning means generally when the data set is you have a huge data set, then you will go for the deep learning approach. So what is the difference between traditional models and the AI? Traditional model, if you look at, for example, we know the Tarjagi bearing capacity theory and the Tarjagi concentration theory. Already we have ready-made equation. You give the value, you will get the bearing capacity value as well as some values. But in the coming to the AI approach first to develop the model. So there are two steps are there. If you look at, one is the training phase, that is use some of the data set, that is you are training the model, and next is the testing phase, that test the model. That means you train the model first, you develop the model, and then you test it. If the testing part, if the model is performing well, then you can use for the other data set. So there are two phases programming is there in the AI model, but traditional model already it has model developed, already analytically model developed, and you give the equations, and then you will get the value. For example, if you take the bearing capacity problem or liquefaction problem, so just like a serial in this approach, if you give the all parameters, soil properties and earthquake parameter, then they will tell whether soil will liquefy or not liquefy by using the calculation of the CSI error. But in AI model, you have to first train the model, and then you develop the model. Then you can use for the future purpose. So this is the basic difference between the traditional approach and the AI approach. So how to develop the AI approach? So generally, if you look at the data set, generally in geotechnical engineer, for example, liquefaction generally data set come from the literature data set, and other things we can do a lot of experiment. That's like SPT, CPT, all this. So data set is come, then we do the data pre-processing by segmentation, normalization, and then we train the model. After training the model, after configuration, then we use the new input data set. That means if you look at this is the new input data set, and that you use in the model. So if your model is for the new data set is coming good, then you can then the model is reliable. But if it is not good, then again you change the training algorithm, and then again you train the model again, and then you have to get a better model. So now I come to the sample application, that is the uplift capacity of suction Kaizen. That is the different parameters. What is the input parameter is that is the loading rate parameters, and the L by D. So whatever the parameter is, and D by L, undrained shear strength, and theta is this one, and the output is the uplift capacity. So this is actually the problem actually I am taking as a to be given on sample application. And so this is the inputs we have loading parameter, L by D, D by L, undrained shear strength, and the theta. Output is the uplift capacity. So I have used four models. That is the first one is the Gaussian process regression. In this case, data is generally assumed as a follow the Gaussian distribution. Then next is the multivariate adaptive regression spline, and next one is the extreme learning machine, and last one is the minimax probability machine regression. So these four models I have used to determine the uplift capacity of the Kaizen foundation. So Gaussian process regression actually in this case, that every input variable assume that follow the normal distribution. So if you combine all the inputs and the output, then it will come that is also follow the normal distribution. And then if you give a new input, for that also it follows normal distribution. Based on that, they predict the data set. So in this case also they calculate the mean and covariance function. Regarding to the Mars model, this is quite interesting. If you look at that, for example, you have a data set that follows this type of trend. So this is the X is the input and Y is the output. If you look at, in this case, if you just draw a straight line, if you have a linear equation, then if you look at that, if you consider this data set, the huge amount of error will be there because your actual prediction is there. So, and in this case, if you see that in this case, your lower prediction, but if you can use 2-3 lines in this case, then your error will be reduced. That means if you first use one line up to this point, then you again use another point, and then again use. So if you look at this here, actually, here automatically if you use the straight line, but error will be less because this is your actual prediction, and the actual data is there. So always the error is reducing here. So in this case, you can get the lesser amount of reduction of the error. So here you are changing the new line, that is called the knot location. I will come to that next part in the knot location. So if you look at, this is the concept of the knot and basis function. If you look at, so your actual data is following that X and Y, that is following in this trend. So I have used one, this is one knot location, another knot location is here, another knot location is here. every not location, the basic function will change. So if you look at that, I have given two examples of the basic function. One is the BF1 and BF2. So this max 0, x minus 6.2. That means if you look at this, up to x 6.2, that all the value will be 0, basic function will be 0. Then when is cos x 6.2, then your basic function will increase the value. Similarly, if you take the mirror of this basic function 1, then if you look at that, when your value is up to 6.2, it is reducing, it is coming to 0, and after 6.2, it is value is 0. So basically, it's a mirror type of function is there. That is the basic function. So that is the Mars model. When you are constructing Mars model, two things is very important: how we choose the knot and how we choose the basis function. Next model is the minimax probability machine regression. This is developed basically when you do the prediction, we have no control over the future prediction. For example, if you can predict any SPD data cannot be negative. So here actually you are giving the bound that your data set should be within some bound with some probability. So here actually input and output is given by this equation, that is y is equal to output and beta is the weight, n is the number of data set and k is the kernel function, x is the input and b is the bias. So how it's doing, if you look at this figure, so first one data set is obtained by shifting all of the regression data plus epsilon along the dependent variable y-axis, and other data is obtained by shifting all other regression function minus epsilon the dependent variable. And then you do the classification between these two data sets, then you will get the regression function. So basically in this model, you are giving some bound that our data set will be within this tube. That is the maximum probability. It is not guaranteed that the data set will be always this bound, but you are maximizing that probability that the data set will be with this tube. Next adapted technique is the extreme learning machine. So in this case, actually generally there are traditional neural network is there. So if you do the traditional neural network, that is the one input layer, one hidden layer, and the one output layer. So this is developed by the Huang and his team. So in this case, the weight generally when the input layer to hidden layer weight, they are giving the arbitrarily. But when you are calculating the weight between the hidden layer and output layer, that it has been calculated by the analytically. How I will show in the next slide. So basically, if you take a single layer hidden layer feed forward neural network, that is the summation of I to n bar, and beta I is the actually weight between the weight vector. Beta is the activation function of the hidden neurons, and beta is the weight vector. That means this weight vector you have to calculate by analytically, and W actually G is the your activation function, and W is the weight between the input layer and hidden layer. The input layer and hidden layer weight is W, and B is the bias, and T is your target. That means what is the output? In this case, the uplift capacity of the suction causal, and X is the input, that we have 5 input. So how we are doing that? Above equation can be modified that if you take the T is equal to your target vector, and H is equal to actually that is the hidden layer output matrix. That means W1, W2, that is all are already defined, and the G is the activation function that already I have defined. But beta you have to determine, that is the beta. Beta is the actually your weight between the hidden output layer and hidden layer. So if you do this, if you take the matrix form, then beta will be H inverse into T. So beta is the more Penrose generalized inverse. So if you do the beta in this way, analytically you can determine the beta value. That means weight value. But in traditional neural network, this has been done by the traditional approach by during the minimization of the error. So that is the comparison between the neural network and the extreme learning machine. So this is the data set. As I have already told, that data set has been collected from the one paper Rahman et al. In 2001. The data set contains information about L by D, ACU, TK, and theta, and D by L, and a P measure, that is the uplift capacity. So the data set actually, I've tried to have a correlation between the data set. So if you see that this is the correlation, that means if you take the L by D and L by D and L by D, if you see that there will be 1. But if you look at this L by D and ACU, then it will be minus 0.091. L by D and TK will be 0.33 and L by D theta is 0.19. So this is a basically correlation diagram of the all input variables. That means we can find out that how much data is correlated with the other input variables. If you look at that, this all coordinate is 1 because that is we are comparing with the same data set. That's why it's coming 1. So that is the one advantage of this AI model, that the developed Mars model gives very nice equation to determine the uplift capacity of the suction caisson. That is, the uplift capacity is equal to 0.006 plus m is equal to 19. Cm is the coefficient of the basis function plus Bf. So basis function already I have described. Now if somebody wants to use this equation for the practical purpose, so you have the all input L by D, theta and Tk and D by L and SU also. Then you put all these value in the BF1, BF2 and BF3, BF4, BF5 and BF6, BF7, BF8 and BF9. And then you put this value here, then you will get the value of the output capacity here. So, so in this way, this equation can be used for the as a practical purpose. So here actually one thing I forgot to tell you, that I have used around 51 data as a training data set and remaining 11 data as a testing data set. So here actually I have tried to compare the data set with Taylor diagram by various model. That the question is that which model is the best model. So if you look at this figure, that this is actually our base model, and these all lines are actually your root mean square error, and that circle line is the correlation. That means if so the correlation is 0.99, 0.95, it is reduced. That means in this scale it is 0 to 1. So if you look at this perfect model, means it will be close to the horizontal line, but it will be close to this 1 actually. And but if you look at that, data set is very close to this line. So in this case, same thing have been happening in the training as well as testing also. Okay. Now this is called a Taylor diagram. Now there is another cost validation we can do by the RDC curve, that is called the irrigation error characteristics curve. In this case, that we have plotted the accuracy versus absolute deviation. Absolute deviation means what is your model prediction and actual value of the uplift capacity. So when the absolute deviation is 0, means that is the perfect model, and accuracy means 1. That means if it is a perfect model, then your curve will be from here to here. So that means in this case, so there is two things is there. One is the area over the curve and area under the curve. Area over the curve means upper portion of the curve, and area under the curve means lower portion of the curve. So if your area over the curve value is very low value, is close to 0, then your model is good from this graph. So if you look at this, almost every model has given almost close to 0 value, so that you can tell that, and that every model has a capability to for the prediction of the uplift capacity suction caisson. So, and another thing is that you can that one Mars model has given very nice equation, so that people can use this equation as a for the practical purpose also. Now coming to the future application of the AI, I will give some future application of what we can apply the AI for the future application. One thing, if you look at that, nowadays people are using also hybrid machine learning model, hybrid artificial intelligence model. So what is the problem of traditional AI model is that if you look at, so basically in every AI model, generally we are minimizing the error actually. We are every time we are calculating the actual value, we have actual value, and we are calculating the model prediction, and based on that error. So actually our primary aim is that the error should be close to 0 value. That means what we are doing, basically we are doing error minimizing. So error minimizing means, but the minimizing value will be not 0. It can be minus also, minus 1, minus 2 also. So sometimes what is happening, actually our aim is that error should be there, because it will be 0. But when it goes to 0, that will be not 0, our main aim. So traditional AI model, actually sometimes we face this problem. Traditional AI model and traditional optimal algorithm, when the data set is very huge, that we face the problem, we don't get the good result. So in this case, what we do the meta-heuristic optimization and AI. Meta-heuristic optimization means there I can define that what is our main goal. Our main goal is that our function should be close to our objective function, our error function should be close to 0 value. So that's why if you clump these two, AI and meta-heuristic optimization, then we can get the hybrid AI. So hybrid AI we can use for the when the data set is very large amount of data set is there. There we can use the hybrid AI. Next, another thing is that recently I just one paper that where we can site system of the wind farms. So when you are selecting site for the ultimate output of the wind farm, that depends on the various criteria. One is the environmental criteria. If you consider that is the wind speed, elevation, slope, distance to fault zone, and distance to landslide zone, and distance to bird mitigation plan. And economic criteria, the distance to transmission line and distance to main roads. Social criteria, distance to protected zones and distance to water bodies, distance to settlements, and distance to airports. So these are the all criteria. If you combine all these criteria, that is basically a multi-criteria decision-making problem. So in this case, if you can use the AI model, and then you can train and test the data model, then you can get the for a particular site, you will get that where if you can put the wind farm, wind turbine, and that will give you the maximum output. So that is a multi-criteria decision-making analysis by using AI model. Next thing we can do that prediction of the wave-induced liquefaction. Generally, if you look at that, seed and liquid approach is there, that is applicable only for the earthquake-induced liquefaction. But wave-induced liquefaction, if it is there, then we don't have any traditional approach is there. So here you can use that AI also. In this case, input will be the water depth, wave height, wave direction, wave length, soil permeability, and degree of saturation and porosity. Maybe some other parameter also, but in my knowledge, I know all these parameters. And here actually, if you take some case studies where the liquefaction observed or not observed has been observed, then you can develop the AI model. So this is basically a pattern recognition technique. That means your pattern recognition and binary type of problem. That means you are developing whether liquefaction will be observed or not observed. So after developing a model, then you can take this developed model and you can take any site and then you can use this developed model. Next is that you can we can detect the scout also. The scout is a huge problem in the wind turbine foundation, and it depends on the diameter of the piles and water surface, water depth, and the seabed also. So AI can be used for the classifying between the scout and non-scout. So AI, that also it can be used for the classifying the scout and the non-scout also. Next, so sometimes which type of foundation we will use, we have a lot of things we have to decide that what type of foundation we use for a particular wind turbine. So AI model would use can be, you take the various characteristics of the wind turbine and the site condition as an input. Then the jacket design, jacket type of design variables would be outputs. Then you develop the model, and then you take a new site and take all this input and give the input, and then you can determine that what type of what will be our, if you use the jacket type of foundation, then what will be our design variables. So what is the take-home message that I can give some conclusion in the take-home message that first is the very important thing is the performance of AI is data specific. That means you cannot see, I have used the 4 models, so there are many models are there. So you cannot tell this is the best model and use for all the offshore geotechnic problem. That is not the case. It's a data specific problem. How the data is you are giving, quality and quantity of the data is the most influence factor for the performance of the AI. Second point is also very important. The result of the AI should be analyzed thoroughly and decisions should be taken based on the practical experience. That means you cannot use the AI result blindly, that just you get the result and do the things. You use your practical experience also and visit the site. You have to, when you are taking the final call, then you have to use your own judgment also. Second, but third thing is also very important that AI model can reduce the cost of the project by reducing the number of soil testing procedure. it can reduce the cost of the project. So that's all. This is my presentation. Thanks.
Thank you, Piyush, for your excellent presentation. Any questions?
Somebody goes that file files and arbitration comes and the European judges are asking for explainable AI. What is the scope of explainable AI here?
Explainable AI means you have to, that every generally AI has been criticized by the black box model, but explainable AI means when you are taking some parameter, that will be some, you will give some judgment that based on that we are taking this parameter. That means you will explain the whole procedure, physics-based model actually. For example, if you take the shallow foundation of bearing capacity of the shallow foundation problem, okay? In this case, when C will increase, phi will increase, automatically your bearing capacity will increase. So in explainable AI, they will use this concept. They will not take any other concept.
Some indices are there. In what resources they use? Shapley index and then transformation.
Shapley index is calculated to determine the sensitivity analysis. Which parameter has the maximum effect?
Some more questions? Any more? Okay. Just one question. Suppose if I need to use AI to predict a scenario which has not been thought of before, what would be the best way to do it?
Not even thought before.
Yeah.
Means then you go for the unsupervised machine learning, or means that means output is
output. We don't know what would come. I mean, I don't have a data set. I don't know
within this range.
We have to decide how it looks like based on some thought process.
And then you can go for the unsupervised machine learning model. Unsupervised k nearest neighborhood, all this technique is there, whichever is unsupervised. That means output is not known to me. Okay. So in this case, you can use the clustering technique, all this.
Okay, thank you. Fine. So if there are no questions, we again thank the speaker, and he has given us some time for refreshments before we go for the cultural program, I think. I hand over the, yeah. So there's a memento for you, Piyush.
I invite Professor Sunil Biam to hand over the memento to our session chair.
Well, so we have come to the end of day one technical program. Yeah, I hope all of you will agree with me that it was very enriching day technically. Our knowledge has been enhanced and a lot of experience by industry professionals and researchers from academia have been shared, and the research outcomes. So we had a wonderful day, and yeah, so we need a break. So we will have a small break. Say now it is 5:20, maybe 6:30 p.m. Oh, no, Dr. Parsardi is asking whether you really need a break or can we continue with the program. Yeah, so we will have a small break. So please visit the exhibition stalls. Please visit the exhibition stalls, and there are couple of announcements. Those who have not collected the registration kit, the registered delegates, those who have not collected the registration kit, can collect the registration kit from the registration desk just outside this hall. And the registrants who need a receipt for their payment, tomorrow morning 8:30 to 9 a.m. we will be issuing the receipt, and during tea break time and lunch break also we will be issuing the volunteers will issue the receipts for any payment that you have made to the ISOG account towards sponsorship or registration. Going to present you an award-winning Bombay Atta. That is a very unique puppet show with the Yakshagana costumes. The artists are already here. They have been doing their preparations for half-day preparations are going on, and by 6:30 p.m. they told they will be ready. So please refresh yourself and come back to experience the rich traditional heritage of Tulu Nadu. This land, I don't know how many of you are aware, even though the language of Karnataka is Kannada, this specific region has a very ancient language named Tulu. All these local people will speak Tulu here in Dakshina Kannada and maybe in some parts of northern Kerala in this specific region, and this land is called Tulu Nadu, which has a very unique, rich cultural tradition, and they are going to present. We are sure Professor Sunil has been coordinating with them. We are sure that you will enjoy it. Yeah, then after the cultural program, we will be having a great grand banquet dinner which you should not miss. So we have put all our efforts to give the best hospitality. So please enjoy the banquet dinner with the beverages. Loosen, so we have been sitting through all the technical sessions. So loosen your body, shake your legs. So we will have a good celebration tonight. But please don't forget, tomorrow morning 9 a.m. we are having technical sessions. So please be on time. So we will take a small break. See you soon at 6:30 p.m. for the wonderful cultural program. Thank you.
यात वरपचे पर जाता सर कशाला
Index of 12. His research has contributed significantly to the fields of offshore structures and geotechnical engineering. With this brief introduction, I present before you Dr. Niranjan Shah, and I request him to conduct the plenary session 2. Over to you, sir.
Thank you, everybody. Thank you, everybody. Thank you, organizers. So this is plenary session 2, and it will be there will be 2 speakers over here: Dr. Brent Robinson from Pile Dynamics and Professor P.G. Shamui from Civil Engineering Department of NIT Patna. The first one is by Dr. Pile Driven Pile Drivability in 1999 as a research engineer, and then from KC Western Reserve University. Brent is a member of ASC.
I've always wanted to visit. But be that as it may, this allowed me to do a couple of events at the same time or on the same day in very different places. So I appreciate your patience with the remote presentation. And today we'll talk a bit about pile drivability, particularly driven pile drivability. First, walking through the way that we assess the drivability of piles as when we think about driven piles, generally speaking, a jacket that's brought on a material barge and put into place on site, with then a pile that's stabbed and driven above the water surface. And so, typically the top of the pile extends above the water line to the top of the jacket, where it then gets welded and fixed in place. We've also done over the years, and I know it's a common design method in India and across Southeast Asia, some of the skirt pile jackets, and we'll give an example of that here a little later. But a skirt pile jacket where the tops of the piles are driven beneath the water surface, and the tops of the piles are connected to the jacket bottom and kind of pinning that jacket in place in deeper water lines. We also can think about kind of offshore geotechnics on the nearshore environment, where we have the same marine clays, we have the same and marine alluvial sands and other materials that are in place and that we need to drive through. But for nearshore structures, those are things like jetties, things like piers, docks, and all of the the barge-driven or barge-installed or trestle-installed structures that might be out there. And in the last, we'll say, 10 to 15 years, particularly in Europe, and now increasingly elsewhere around the world, there's been a move towards monopiles, which are very large diameter open-end pipes, typically on the order of many meters in diameter, say 5, 8, 10, even more. And that's kind of driven a new round of innovation, first in the increasing size of the hammers to drive these very large piles, as well as different means of instrumentation and models that are needed to get these much larger piles in the ground. And there's also some movement in our profession looking at how monopiles can be not only installed with an impact-driven hammer, but also with vibrator hammer. And so when we think about the process of completing driven piles, we generally complete the initial pile design in conjunction with the jacket design. Then we size the hammer based on a wave equation drivability study. And for those who are maybe unaware, the wave equation program uses either a lumped mass model or a model based on the method of characteristics to model a very long, slender rod, which consists of first the pile, but also the hammer's driving systems, its helmets, its inserts, its pile caps, and the hammer that attaches on top of it. And so that's kind of one long single section. Once we've done that drivability study, we might go back and refine and pile that and refine the design of the jacket in the pile, where that might create some iterations between what hammer is needed, what pile wall thicknesses are required, what stick-ups are required, and we kind of go around until we have an acceptable solution. Once that contract is let, or once the jackets or piles are fabricated and then sent out to the job site, to the installation site, during construction, there are often scenarios where we monitor piles, first using something simple like blow counts or a penetration rate, and then also taking it and looking at the behavior of the hammer and the behavior of the pile as it's driven into the ground using high-strain dynamic testing. That testing allows us to estimate a static resistance to driving, which is the apparent first total resistance, and then later estimating out the static resistance at the time of the installation. And occasionally we'll do longer term restrikes, although in the offshore environment that's limited to usually a matter of hours and less a matter of many, many days. Although we're seeing some movements in some parts of the world to try to get longer term restrikes or longer term tests on piles that have been already installed. And then ideally, either within the company itself or in a scenario like the Indian Society, we use those results to then help to inform our future designs and to inform our future wave equation studies, so that we can, I guess, basically do better the next time in the way that we set things up. And so in thinking about that, we can imagine a pile drivability analysis kind of consists of three main points. First is to perform a static soil resistance calculation, which is something that we need to do axially and laterally to begin with in order to determine the pile design and where the loads will be shed from the structure into the soils. And so we do that as accurately as we possibly can, using models that have hopefully, and analysis methods that have hopefully been calibrated to the site itself. And we look at that at different incremental penetration depths. First, determining if it's sufficient to withstand the applied loads, but second, to see if we can actually install that with the hammer. And to do that, we then perform a wave equation analysis at each depth using an ultimate resistance that we determine from that static soil resistance calculation, often taking the long-term static soil resistance and reducing it some amount to account for disturbances that are happening as we drive the pile into the soil. Once we run that model, we can plot the ultimate resistance, we can plot the blow count, and we can also look at things like maximum driving stresses and the hammer performance, each versus depth. And so this drivability study is a means of predicting the driving effort and the energy applied for that driving effort before we get out into the field. And so of those kind of three steps in our GRL wave equation program, there are a number of different soil resistance calculation methods that we can take a look at. Some that are based solely on soil type, which we would typically not necessarily recommend for an offshore environment. But I guess the more common results for an offshore type presentation would be the original API method, and then the API RP2A methods, which expanded beyond an effective stress and total stress type model to a larger number of cone penetration test-based direct design models. And that includes things like the Imperial College method, which was developed largely for the North Sea and the clays and sands that they find there. We also have the University of Western Australia's method, designed for those piles more in Southeast Asia. Fugro in their 2005 method, as well as the Norwegian Institute of, the Geotechnical Institute's method, all of which are applying slightly different factors in slightly different ways to determine the CPT. In the last several years, we've seen an increase in the popularity of friction fatigue models to estimate the driving behavior. And we've now instituted the Ullman-Hamra method, which effectively models an ability or the loss of strength of the soil due to repeated loadings. And so we treat the static resistance or the soil's resistance to driving not as a fixed thing, but as something that is gradually reducing and kind of meeting a lower bound as we continue to drive. And so that Ullman-Hamra method and a built-in GRL friction fatigue method are also available. So effectively, we're trying to decide which of these we're going to use, or which suite of these we might use in order to run our analysis. And so when we think of the flow of a drivability study, we start with our input, putting in the geometry, choosing a hammer, and entering soil borings. From that, we model the hammer and the driving system. Then we can choose our first depth that we want to analyze. From there, we model our pile length at the depth that we're analyzing it. So that's likely shorter at the beginning of drive and longer at the end. And we place that model put that model in place and then calculate an ultimate resistance for that first soil resistance level. And so initially that's probably with a fully reduced soil resistance to driving. And then we might go back later and calculate it against some sort of intermediate or fully the long-term resistance. If we suspect that there is a scenario where we need to drive that pile after a long waiting period. Then we run the numerical analysis, and that then asks if we want to check that longer term resistance after checking the short term. If we do, we go up to the next analysis method. We run our analysis again, and then once we're finished with that, we go on to the next depth. And so each of these is looking at a bearing graph for a couple of fixed capacities at each depth that we're looking. That increased depth then turns into potentially a longer pile length and an adjustment to the model as to where the pile tip is in the soil. Once we do that, we can enter the program and kind of see where things are set up. There is a large database of hammers that we can choose from, or we can build our own if there's a hammer that we haven't seen before. We can also see the driving helmets and cushion information, our geometry of our pile, its length, its final penetration, as well as the driving scenarios that we want to put in. And so here we're showing a pile driven on a batter with a fixed jacket, a hammer with offshore leads sitting atop it, and those all kind of work to determine different aspects of our driving scenario. And so once we have that, we get a pile drivability result that looks at the distribution of soil resistance at the time of driving. And so this is an example with a reduced shaft resistance as well as a reduced end bearing, likely to indicate some partial plugging that might be occurring in this open end pipe that we've modeled. And there, in this non-friction fatigue model, we can also see the blow count is a red line, kind of gradually increasing, similar to the soil resistance to driving. We would also note that we're seeing a few different places where we have very abrupt increases in resistance, as those are likely indicative of weights that are occurring when we splice or add length to the pile. In the center, we're looking at the maximum compression stress in red, and we can also turn on an analysis method that looks at the maximum bending stress at the top of a fixed jacket. And so going back, again, we said that there is that the weight of the hammer is suspended atop the pile top, and as we place that, there's because of the angle it's on, we'll have a component of the weight of the hammer that's along the length of the pile, but also a component of the hammer that's perpendicular to it. And that will start to apply an additional bending moment that's at the location of the jacket. And if we don't consider that, and we run the hammer at full strength, then we potentially create a problem where we overstress. So we can look at that scenario in our drivability studies, and trying to limit the overall stress to below the yield stress or below a percentage of the yield stress of that location. Keeping in mind that for drivability studies, we are often looking at a worst case scenario, i.e. we want to make sure that we have an adequately sized hammer to drive the pile, even if it is a scenario that we think is less likely to happen. Because driving, an easier driving situation is something that can be easily overcome in the offshore environment, but it's very difficult to get a larger or a different hammer out if the one that we've selected is inadequately sized. And so in looking at this, we can see, again, increases in the energy that are being sized to allow for the blow count that's being observed on the site, and also to determine whether we can run the hammer at higher energy levels in spite of the compressive and bending stress. Another part of the drivability study that has also become increasingly used or increasingly discussed, I guess, particularly in the offshore monopile for wind foundations, is the analysis or the inputs that can be generated for fatigue analysis. While we don't do a fatigue analysis because there are so many different ways that people approach that, there are a number of ways that we can look at how the fatigue
Thank you.